Cambridge Assessment Admission Testing, 6th Term Examination Paper, Step 2019, Paper 1, Section B, Applied Mathematics. Question 9. Hi, this is Babak. In this video, I am going to solve question number 9 of this past paper. Let us read the question for you first. A box has the shape of a uniform solid cuboid of height h. So in this diagram, I am only concentrating on a cross-section of this real picture. So this rectangle ABCD is a cross-section of the box. So according to the information given in the problem, the height here from A to D is considered to be h. And with a square base of solid B, where h is greater than b. So this length from C to D, which is the width of this of the base of this box, is b, and it is assumed that the height h is greater than the width b. Okay, it rests on a rough horizontal ground. A light ladder, so this is representing the ladder in my picture, has its foot on the ground and rests against one of the upper horizontal edges of the box, which in this case is this point A, making an acute angle of alpha with the ground. So this is the angle alpha, where h is equal to b 10 times tangent alpha. Okay, so there is a point here. This is an indirect way of telling you that the distance from D to O is also equal to B. Why is that the case? Let me explain it just here. So if you consider this right angle triangle OAD and concentrate on tangent of alpha is equal to the opposite side of, so this is angle alpha, the opposite side is AD, so this becomes AD, divided by the adjacent side, which is DO, okay? Okay, now, on the other hand, from here, you can see that tangent alpha is equal to h over b, yes? So instead of tangent alpha, you can write h over b. So this means that we have h over b. On the right hand side, if you see here, AD was assumed to be h, so that's the height of this box. So this is h, and then I have my DO, yes? And then it is clear that the denominator should also be the same. So it means that DO is equal to b. So as I told you, this is an indirect way of saying that DO is equal to CD is equal to B. Okay. The weight of the box is W. So because it has been assumed that this is a uniform box, so the center of gravity coincides with the geometric center. So this is why I have drawn this vector W from this center. That is the weight of your box. There is no friction at the contact between ladder and box, so there is no friction involved here. A painter of weight kW climbs the ladder slowly. So the painter starts climbing the ladder slowly. Neither the base of the ladder nor the box slips, but the box starts to topple when the painter reaches height lambda h above the ground, where lambda is less than 1. Okay, so this painter starts climbing up. At some point here, then this box starts toppling about point O, okay, toppling around. Okay, so at that point, the height of the painter to the ground is assumed to be lambda h. So this is why I have written from P to Q is lambda times h, and the weight of the painter is K times W. In the first part of the problem, we are supposed to show this equality where R is the magnitude of the force exerted by the box on the ladder. So this is the vector, force vector that is exerted on the ladder by the box. But these things that I have written here are not the real forces, these are the magnitudes of forces. So the first the first part of the problem, we want to show that R is equal to K times lambda times W times cosine of alpha. Okay, and now because it has mentioned that the ladder is light, so it means that I don't need to consider the weight of the ladder. Okay, assume that the ladder is weightless. Okay, my strategy to solve the first part of this problem is to look at the equilibrium conditions on the ladder. Okay, so first I need to know the forces acting on the ladder. So one of them, according to the problem, is the force exerted by the box. The other one is the force that is actually acting on the ladder because of the reaction between the painter and the ladder. And it has been assumed that the magnitude is K times W. There are also two other forces, actually the reaction force from the ground, which can be resolved into two components. One of this is the normal vector N, and the other one is the friction force. So these are the four forces acting on the ladder. Immediately before the box starts toppling, the ladder is in the equilibrium. So it means that the net force acting on the ladder should be equal to 0. The net torque acting on the ladder about any chosen origin should also be equal to 0. Of course, I want to use the second condition to, as you see, to be able to solve this problem, this part of the problem. So the point that I will choose for the rotation is actually the point O. Because if I choose this point O, then I don't need to know the magnitudes of this force N and the force F, which I don't know at this stage at least. Okay, why this is a good choice? Because then if I choose this point, the torque of N and the torque of F about O would be 0. The perpendicular distance of the point O from the line on which N and F lies is equal to 0. So the torque of N about O as well as the torque of F about O is equal to 0. So there are only two forces that have non-zero torques about O. One of them is R, one of them is KW. And of course it is clear that this force will try to rotate the ladder in the clockwise direction, and this force will try to rotate the ladder in counterclockwise direction. So in the equilibrium, the magnitudes of these two torques should be equal so that I can have the equilibrium. Okay, so that's the condition that I want to use. So part 1 of the problem. First, let us concentrate on the magnitude of the torque of this force about O. So the torque I need to write is the magnitude of the force, which is R, multiplied by the distance of the point of rotation that I have chosen for the origin, the perpendicular distance of the point chosen as the origin to the line on which this force lies. So you see that this force R lies on this line, and if I want to find the perpendicular distance from O to that line, that's exactly this distance. Yes, and this means that this distance is from O to A. So I would write it this multiplied by the length from O to A. This should be equal to the torque of this force about the same point O. So it means that I need to write the magnitude of the force, which is KW in this case, and multiply it by the perpendicular distance of the point O from the line on which the force vector lies. Okay, the force vector lies on this line, and the point is O. So the perpendicular distance is this distance here, yes, as you see here. And that is from O to Q. So this means that I need to multiply it from O to Q. Okay, but my point here is to find r. So it means that I divide both sides by OA. So this gives me r is equal to kw and multiplied by OQ. So let me write OQ divided by OA. But if you consider this right angle triangle here, yes, then this OQ is the hypotenuse, which is OP, multiplied by cosine of alpha. So I would write this is equal to KW multiplied by, so instead of OQ, I write OP multiplied by cosine alpha. Yes, and then divided by OA. If I rearrange the terms a little bit, so this becomes equal to KW, and then I would write cosine alpha here, and then I have this ratio OP divided by OA. Now my goal is to show that this ratio is equal to lambda. One way to do this, for me it was easier to do it in this way, use the similarity between these two triangles, OPQ and OAD. So this triangle and this bigger triangle, I'm claiming that they are similar. Why is that the case? Because this angle is 90, this angle is 90. On the other hand, this angle alpha is common to both triangles. So two angles from one triangle is equal to two angles from other triangle. So these two triangles are similar. So it means that the ratio of OP to OA is the same ratio as QP to DA. Yes. So instead of this ratio that I have here, instead of OP over OA, I would write PQ over AD. Yes? But here, because of the information given in the problem, PQ is lambda h, so instead of PQ I can put lambda h, and AD is just h. So instead of AD I can put h. So this becomes KW cosine alpha, and then I will have lambda h divided by h, but now this h and that h are cancelled, so this becomes KW cosine alpha times lambda. And that's exactly the relation that I want to show here. Yes, so this means that I was able to show that this is equal to K lambda W cosine of alpha. Okay. For the second part of the problem, as you see, I'm supposed to prove this equality between parameters alpha, lambda, and k. My strategy to solve the problem is to consider the equilibrium conditions for the box this time. Okay, so first I need to know the forces acting on the box immediately before the box starts rotating about this point C. At that moment, the forces acting on my box is of course the weight W, and then the reaction of the ground, which can be resolved into two components. One of them horizontal, one is the friction force, and the other one is the normal force. And of course, this was the force exerted by the box on the ladder. According to Newton's third law, there would be a reaction force with the same magnitude pointing in the opposite direction. And as I told you before, these letters that I put on these vectors represent their magnitude. So if I have chosen letter R for this magnitude, I have to choose the same letter R for the magnitude of the reaction force. Okay, and again, I know that in equilibrium, which is the case immediately before the box starts toppling around the point C, the net torque acting on the box should be 0. If I take this point as the origin for writing the torques about it, then these two forces are actually passing through point C, so they do not have any effect on the net torque. The torque of F about C is 0. The torque of T about C is also 0. So there are two forces that they have non-zero torques. One of them is R, the other one is W. And if you can imagine that this R will try to rotate the box in the counterclockwise direction about C, and then W will try to rotate the box the clockwise direction about C. So in the equilibrium case, they should actually have the same magnitudes. Okay, so what I need to write, I need to, for the second part of this question, what I can write is that the torque of W with respect to C, let us calculate that one. So how should I calculate? So I need to multiply the magnitude of the force, which of course is W, by the distance of the C to the perpendicular distance from C to the line which this W lies on. So you see, this line is the line on which W lies, and if I want to calculate the perpendicular distance, it would be from here to here, which is half of the width of this box. The width of the box was B, so this becomes B over 2. Okay, so the torque of this force is W times B over 2. So this should be equal to the torque of the other force, which is the reaction force R. Okay, so I need to multiply the magnitude of that force, which is R, by the perpendicular distance from C to the line on which R lies. So you see, the line on which R lies is this line, yes, and this perpendicular distance from C to that line is this distance, yes, which is CS, and for simplicity I have denoted this length by X. So this is X. Okay. If I have an eye on what I want to prove, this relation is independent of W and R. Of course, in the previous case, I can use this. Let me just calculate. Let me substitute this. Instead of W, let me just write W and B over 2. But instead of R on the right-hand side, I can use this relation. So I can write K times lambda times W times cosine alpha, and finally times X at the end. But then it's immediately clear that I can simplify these two W's, and if I also multiply it by 2 over B, so let me do it step by step. So first I simplify W's. What is left for me is B over 2 is equal to K lambda cosine alpha times X. Okay, and then I multiply both sides by 2 over B. So what happens? It becomes 1 is equal to 2K lambda cosine alpha X over B. Okay, so my motivation was to make 2K lambda appears. So here everything is more or less, we are getting close to what we want to prove. Yes, we have 1, we have 2K lambda here, but of course instead of cosine 2 alpha, still I have cosine alpha, but I have also this fraction left. Okay, so from now on I want to concentrate to find this in terms of alpha. I want to write X over B in terms of lambda. Okay, so the geometry is a little bit more complicated here, so let me try to talk about the geometry here. So first of all, you see that this big triangle is a right angle triangle, yes? So if this angle is alpha, this angle would be pi over 2 minus alpha. So this is what you see here, pi over 2 minus alpha. Okay. Now I will concentrate here on this right angle triangle. Yes, and then I can write cotangent of this angle to be the adjacent side, which is from here to here, divided by the opposite side. Okay, I'm not saying that probably this is the only way. You can also think yourself, find the other ways, but this is one way at least works for me. So I would write cotangent of pi over 2 minus alpha in that triangle that I mentioned. So let me also write the name of the triangle. So in triangle MAD, I can write cotangent of pi over 2 minus alpha is equal to the adjacent side, which is MD, divided by opposite side, which is AD. Okay, but you know that cotangent of pi over 2 minus alpha is just simply tangent of alpha. And then if you look here, what is MD? MD is from here to here. So this is from M to C plus C to D. Okay, from M to C, for simplicity, I called it Y. And from C to D, we know that this is B. So this becomes Y plus B. Yes. And the denominator, which is AD is the height, so it's H. Okay, so if I multiply both sides by H, I will get H tangent alpha is equal to Y plus B. But we know that here H is equal to B tangent alpha. So instead of H here, I put B tangent alpha, but this tangent alpha multiplied by this one will give me the square of tangent alpha. So this gives me this gives me B tangent squared alpha is equal to Y plus B. Okay, what can I do now? I can move B to the left hand side and factor a B out, so it becomes B times tangent alpha squared minus 1 is equal to Y. Then I can use the formula for tangent squared, sine alpha squared cosine alpha squared minus 1 is equal to Y. And then I can take the common denominator, so it becomes B sine squared alpha minus cosine squared alpha divided by cosine squared alpha is equal to Y. Yes? Sorry. Make it right, cosine alpha. And then you know the formula that cosine to power 2 alpha minus sine to power 2 alpha is cosine 2 alpha. Here I have the same combination, but sine squared comes first, cosine squared comes second. So that's exactly the same formula, but this one is positive, this one is negative, so the answer would be negative cosine of 2 alpha. And that's good because I need cosine 2 alpha here. So then this means that this implies that Y is equal to minus B cosine 2 alpha divided by cosine squared alpha. Okay, but now what I do, I multiply both sides by a cosine alpha. The left hand side becomes Y cosine alpha. The right hand side becomes minus B cosine 2 alpha, but divided just by one single cosine alpha. Okay. The reason that I did this, because I want now to concentrate on this right angle triangle, this is small one, MCS. Okay, so in triangle MCS, what I can write the sine of my angle pi over 2 minus alpha is equal to the opposite side, which is x, divided by the hypotenuse, which is y. So this becomes x divided by y. But you know that sine of pi over 2 minus alpha is just cosine alpha, and that this becomes x over y. And then this means that y cosine alpha is just simply x. Okay? And then if you compare these two, y cosine alpha is equal to x, and y cosine alpha is this one. So it means that x is equal to this expression. Okay, so I will write it actually on the other page. So remember that we've proved that x is equal to this expression. Yes. Okay, so here what I need to do is to write x is equal to minus b cosine 2 alpha divided by cosine alpha. Yes. Okay, but what we need actually, let us go to the previous page. So here you see that I need to calculate x over b. Yes, so let me take this part with me to the right hand side, to the other page. Yes, and let me just write it somewhere, just put it here and make it smaller. This is what we will need. Okay, so here x is this one, so what I can write is that x divided from this relation, I can divide both sides by b, then I get x over b is minus cosine 2 alpha divided by cosine alpha. Okay, and then instead of x over b here in this relation, I put this expression. Yes, so I put this expression here. So what I have on the left is 1. On the right hand side I have 2k lambda times cosine alpha, but instead of x over b I can plug this expression in. It's minus cosine 2 alpha divided by cosine alpha. Okay, and now you see that this cosine alpha and that cosine alpha are cancelled. So what is left on the left is 1. On the right hand side I will have negative 2k lambda cosine 2 alpha. And then I move this one to the left hand side, and then I will get the same expression that I wanted to get. Okay, so this becomes 2k lambda cosine 2 alpha plus 1 is equal to 0. So that is the relation that I was looking for here. Okay, so that also proves the second relation. For the last part of the problem here, we are supposed to show that the coefficient of fraction mu is greater than this fraction, which only depends on alpha. Okay, so for doing that, let me just bring a small version of this diagram to this page. Hopefully it will work. Okay, so I would copy this here and I will paste it here, but I can make it a little bit smaller so details are not that important here. So okay, let us keep this one here. Okay, this time I want to because in the equilibrium not only the net torque should be 0, but also the net force should be equal to 0. Okay, so now here I will concentrate on the vertical components of forces and then horizontal components of forces. Okay, but one thing is important to understand is that what this angle is here. So you see that the whole angle is 90 degrees. So this angle here is complement to this angle. On the other hand, this angle alpha is also complement to the same angle here. So it means that these two angles are actually the same. So if that angle is alpha, this angle is also alpha. Yes, so that's important for this part of the problem. Okay, so let us concentrate now on horizontal components of forces. So there are one force which is of course horizontal and to the right, and then this force can be decomposed, this force R can be resolved into two components, one vertical one and one horizontal one. Of course the horizontal one has length R sine of alpha because this is alpha. Okay, and then it points to the left. So if I want to write the equilibrium condition on the x direction, so I would write minus r sine alpha plus the friction force which acts to the right is equal to 0. So then this implies that the friction force is equal to r sine alpha. Yes? But of course you know that the friction force is at most equal to the coefficient of friction multiplied by the normal force, which in this case is T. So I compare these two. What I get is that so I get r sine alpha is less than or equal mu times t. So if I divide by t, it becomes r sine alpha divided by t is less than or equal to mu, or equivalently it tells me that mu is greater than or equal to r sine alpha divided by t. And of course this is good because I got an inequality for mu in the right direction. Okay, now let us write the equilibrium condition on the vertical direction. So I have three of them. Yes, one of them is of course T pointing upwards, the other one is W pointing downward, and the other one is the vertical component of R. So as I told you, if this is assumed to be R, then the vertical component alpha here, this length is r cosine alpha, and it's pointing downwards. So if I want to write in this y direction, I would write minus r cosine alpha plus t minus w is again equal to 0. So t points upward, w and r cosine alpha are pointing downwards. Okay, so what I can get from here, I can see that t is equal to w plus r cosine alpha. And then instead of this t, I put w plus r cosine alpha, and what I get is that mu is greater than or equal to r sine alpha divided by w plus r cosine alpha. Okay, so this is a good inequality for mu, but it is not what is demanded in the problem. I need to get rid of r and w in favor of alpha. So this fraction should be a fraction only in terms of alpha. Okay, but we have it. We have some relation in the first part. So instead of r here and here, I can replace this expression. Okay, so I can use that relation and write it's k lambda w times cosine alpha. This is instead of r, but after r I have a sine alpha, so that's sine alpha. And then what I do, I can do the same thing for the denominator. So instead of r, I can write k lambda w cosine alpha, but after r I have another cosine alpha, so these two cosine alpha multiplied together gives me cosine squared alpha. Now you can immediately see that in the denominator I can factor a w out, and this w and that w will be cancelled. So then it becomes k lambda sine alpha cosine alpha divided by 1 plus k lambda cosine squared alpha. Okay, but still there is something to be done, because you see that still k and lambda are here, but I want to have an expression without these dependencies, so I want to have it in terms of alpha only. But immediately I can read k alpha from here. Yes, sorry, k lambda from there. So from here I can realize that k lambda is equal to, from the second part, I can realize that k lambda is minus 1 divided by 2 cosine 2 alpha. Yes, so that is k lambda. So then I replace these k lambdas with this expression, and then I will have an expression solely expressed in terms of alpha, and hopefully I can simplify that to get what is demanded in the question. So let me just continue. So then this becomes equal to, instead of k lambda I put that expression, 2 cosine 2 alpha multiplied by sine alpha cosine alpha, and then divided by 1 minus 1 over 2 cosine 2 alpha multiplied by cosine squared alpha. Because if I here, if you see, I have a sine 2 alpha here, so I need a 2 here to make it sine 2 alpha. So to get rid of these fractions, I multiply the numerator and the denominator by minus 4 times cosine 2 alpha. Yes? If I multiply the numerator and the denominator by this, let us see what will happen. So the numerator becomes positive 2 sine alpha cosine alpha, as I want actually. In the denominator, I will have 2 cosine squared alpha, positive one, and then the other one becomes minus 4 cosine 2 alpha. Yes? Now in the numerator, you have a formula. 2 sine alpha cosine alpha is sine 2 alpha. And then you know another formula, that 2 cosine squared alpha is 1 plus cosine 2 alpha. Yes, so I need to use these two formulas. So in the numerator, I will have sine 2 alpha. In the denominator, I will have 1 plus cosine 2 times alpha. And then, of course, I have minus 4 cosine 2 alpha at the end. But then you see that this positive one with minus 4 of them, it becomes minus 3, and I will get the same expression demanded in the problem. So it becomes sine 2 alpha divided by 1 minus 3 cosine 2 alpha. So therefore, we were able to show that mu, the friction coefficient, is greater than or equal to sine 2 alpha 1 minus 3 times cosine of 2 alpha. And that is what was demanded in this problem. Okay, I hope that this video was somehow useful. If you think that the video was useful for you, I would appreciate if you can give me a thumb up and also subscribe to my channel. And then you can find the link to these questions below in the below the video in the descriptions. You can also find the links to these notes with solutions and without solutions in 2 different formats, PDF file and GoodNotes file. GoodNotes is the application that I use to create these notes. Okay? Until the next video, be safe and goodbye.